Today, we're going to be getting up close and personal with the Bohr model. We're going to be learning a little bit more about electrons, where they are, the kind of energy they have, and what they do. Let's get started. When we look at the periodic table of the elements, one thing we always want to remember, and this is a little bit of review, is that the atomic number is always equal to the number of protons for an individual element. And in a neutral atom, the number of electrons will be the same as the number of protons because those positive charges and negative charges need to balance out. So for example, if we were to take a look at copper, element 29, that means that it would have 29 protons and it would also have 29 electrons. But where do those electrons go? What are they doing? Well, that is where we get to orbitals. In the Bohr model, remember the Bohr model is that solar system model of the atom, also known, that's little boy. Pardon me. Hello, this is little boy. He's huge, he's a chunk, he's blind, and he wanted the window open, so we had to do that. All right, so the Bohr model is the solar system model of the atom or the planetary model. So generally when we think of the Bohr atom, it looks something like this. We have a nucleus in the center, we have our electrons going around the outside in orbits, but we know that's not really the way that it works. It doesn't look like planets circulating around a sun. So how does it actually work? Well, when we're drawing the Bohr atom, yeah, it's going to look kind of like this. But when we're trying to understand where electrons are in an atom, we need to think about it a little bit more abstractly. So electrons are generally in orbitals around the nucleus. An orbital is a region where an electron can most probably be found. These orbitals form a series of energy levels where our electrons are found, and different orbitals have different amounts of energy, and this is going to become really important to us later. The farther away we get from the nucleus, the more energy an electron will have. So electrons that are very close to the nucleus tend to have lower energy, and electrons that are far away from the nucleus will always have more. As we get further away from the nucleus, our energy in those electrons and in those orbitals will increase. Here are a few more orbital facts. Orbitals are represented by principal quantum numbers or N numbers. These start with 1 and they go 1, 2, 3, 4, etc. and so on. There are also letters, which are sub-levels within those numbered principal energy levels. And those letters are S, P, D, and F. Now, as far as Regents Chemistry goes, we're not going to be discussing electron spin and shell-filling order. We're going to stick with the basic quantum energy level numbers. If you want to go into SPDF and we want to have that conversation, I'm perfectly happy to have it, but I'm going to do that in a separate video. So a quantum, Q-U-A-N-T-U-M, is the amount of energy required to move one electron one energy level higher than where it is. Because believe it or not, electrons can move. They can go from one energy level to another energy level. And a quantum is the amount of energy that an electron has to absorb in order to bump up one energy level. So for example, here if we have our first 4 energy levels, this being N1, this would be the orbital closest to the nucleus, on out to N4, this would be the 4th one away from the nucleus. As we go from N1 to N4, our level of energy in those energy levels goes up. So the energy required for an electron to be in each of those levels also goes up. So if I have an electron down here in the N1 and it wants to go to the N2, it would need to absorb 1 quanta of energy. If it wanted to go from N1 all the way up to N3, it would need to absorb 2 quanta of energy. So that's kind of the way it works. We're going to talk more about this a little bit later. So if this is our nucleus, and as we get further away from the nucleus, we have increasing amounts of energy in those orbits. Say we have 2 electrons in our first energy level, and here we have 8 in our next energy level, and we have 1 lonely electron out here in our third energy level. If that electron were to fall down to a lower energy level, it would release the energy that it had absorbed to get up to that third level when it falls back down to level 2. And that energy that it releases would be a photon of light. This is literally where light comes from. Okay, and that's something we're going to talk about more as well, because we can predict how much energy gets released. We can also use the light that is released from different elements as their electrons get excited and fall back down to figure out what those elements actually are. Okay, so we can get into some very complex chemistry here. So electrons are generally in what we call ground state. An atom is said to be in the ground state when all its electrons occupy the absolute lowest available orbitals. When we look at the periodic table, all of these electron configurations, and I'm going to talk about that now, are ground state configurations. So for example, let's start here with carbon. If we look at carbon, the electron configuration is written in the lower left-hand corner of the box for carbon, and it says 2-4. What that means is the first energy level, or the first orbital, contains 2 electrons. The second orbital contains 4 electrons, and that accounts for all 6 of carbon's electrons in the carbon atom. If we were to look at iron, here we've got 2 in the first energy level, 8 in the next energy level, followed by 14 in the third energy level, and 2 in the last energy level, or 2 in the last orbital. This would be its ground state electron configuration, or where all the electrons are in their lowest possible energy levels. So one thing to remember is that every shell has a limited capacity for electrons. They can only hold a certain number. The first shell has a maximum of 2. You cannot cram more than 2 electrons into the first shell, no matter what you want to do. The second shell, or second orbital, has 8, and the third has 18. The fourth can hold 32. As we go up, we generally see an increasing number in the number of electrons that each orbital can hold. But it doesn't go straight in this order. It has to do with sublevels and the spin on the electrons. If we're in the first 20 electrons, the order is like 2 in the first level, 8 in the second level. The third level will only fill with 8. The fourth level will fill with 2 before we come back to the third level and start building up to the 18. It starts to get real complicated, which is why we're just going to stick with the numbers for now. So on this periodic table, let's take a look at a few sample elements, and I want you to tell me what the electron configurations are. So what would the electron configuration for nitrogen be? If you said 2-5, you would be absolutely correct. The first orbital has 2, the second orbital has 5. Let's look at the electron configuration for calcium. Element number 20. What is the electron configuration for calcium? Calcium would have an electron configuration of 2-8-8-2. Excellent. Let's come over to germanium. What is germanium's electron configuration? So germanium's electron configuration would be 2, 8, 18, 4. So whatever is written here on the periodic table for the electron configurations will always tell you the ground state configuration for that element. You can see as we start going down the periodic table, we get more shells. I'm going to let you in on a little secret, a little mystery of the periodic table. Are you ready? These numbers down the side, these are period numbers. And depending on the number of periods an element has, that tells you how many shells it has or how many orbitals it has. Here in period 4, we have potassium. Potassium has 4 orbitals. Rubidium below it in period 5 would have 5 orbitals. Okay, that's a great hint to know. Now, when we get down, let's see, where does it happen on this one? When we get down to francium, when we get down to our 7 shells, you'll notice we don't have 7 numbers here. We only have 5. 18, 32, 18, 8, 1. This doesn't mean that we're starting with 18, okay? Once you get to 7 shells, it's implied that the first 2 shells here are 2, 8. So the actual electron configuration for francium would be 2, 8, 18, 32, 18, 8, 1. So what would the electron configuration for dubnium, element number 105, what would it be? So it would be 2, 8, 18, 32, 32, 10, 2. Okay, so if you see a dash as the first thing in the electron configuration, that tells you that they don't have room to show you the 2 and the 8 that come first, but they're there. You just have to fill them in for yourself. So that was a short introduction to the electron. Join us next time when we look at what we can do with these electron configurations, what valence electrons are, and how to draw Lewis dot structures. Thanks.